about how can we generate single sideband and how can we demodulate single sideband. Here are just summary. So for single sideband, right, we have bandwidth the same as the original message. So my bandwidth efficiency is the highest. Also power efficiency, 100%. So this one we can consider the best, right, the best in AM family. For the receiver side, we use coherent detection, the same as double sideband suppressed carrier. Okay, so those are the things. Here, some bad things about single sideband. It's difficult to modulate wideband message having low frequency components. So this one is related with my two generating method. So we talk about, we have so two methods we can generate single sideband. If we use single sideband, we need our signals. Like this, right? Your upper and lower sideband, there are some guard intervals. So we want no low frequency components in your message, right? In X, in FT. So if there's no low frequency components in my original signal, we can use a filter and remove one side. For phase shift method, right? I don't care about if there's the DC, right? Or no. Okay, right? It's okay. However, if you want to shift your signal by 90 degrees for a wideband signal, it's difficult, right? You learn about different filters, right? Different operators. There is always a dynamic range, right? So in this range, you have linear regression, 90 degree shift. However, off this range, you're going to have something weird happen. So if I have low frequency ODC and wideband, difficult to modulate. So this is the sentence about has low frequency components and also wideband message. Generate single sideband will be really hard. And the envelope, right, the message will be really difficult to plot. We only try to plot sinusoid as a message, right, for family signal. Okay, so we're going to talk about the last one in this family called ESP, vestibular sideband. This is the last one and similar to previous. We talk about why and how. Why is modulation for single sideband sometimes really hard. But if we use VSB, can make those special cases, those very difficult cases for single sideband much easier. So we talk about what is VSB, how to do it. Okay, why modulation we just talked about. Single sideband generation. Difficult, right? Very difficult, pretty complicated, especially for wideband and this DC component signal. It's hard to generate. So if single sideband filter cannot be implemented, for example, low frequency there, it's really hard for us. For example, right, broadcast radio, it has pretty wideband. High-speed data, so both wideband and also data generally they have very low frequency, right? If you plot or triangle waves, right, spectrum, it has pretty high low frequency. Sync function, right, is your spectrum. So we cannot implement single sideband. There is an alternating way, Westgale sideband modulation. And the filter we use it, also called Westgale sideband filter. So let's look at what we do. Any problems, any questions so far? So VSB is a compromise between single sideband and double sideband. So we do not completely, right, remove one sideband. We partially reduce it. So compared with double sideband, it has smaller bandwidth, so reduced bandwidth compared with double sideband, and much easier to generate compared with single sideband because this special filter is much easier to implement. Okay, let's look at what is this special filter. Let's give a filter. This picture actually shows what does my filter look like. So this is ideal, right, sideband filter. My filter is, this one's pretty close to Butterworth filter, right? So you have not very sharp, right, from pulse to block. However, it's kind of odd symmetry when we talk about how we can use odd symmetry in my demodulation part. So this is the special shape. I want to remember special shape for Westgale sideband signal. Then we talk about background music. Let me go over here. So it's hard to plot the screen. Let me plot over there. So if we can add several procedure before that. So this is my original one, right? This is this is my original signal. Let's see. We have double sideband suppressed carrier. And we have this special filter, right? Special filter. So we have this special bandpass filter. Special bandpass filter to filter my double sideband suppressed carrier signal, and we get something like this. So you do not have the original upper sideband. You have the modification of your upper sideband. Right. So this is my modified. Or maybe. Next picture. Okay. This one is less confusing. So the first one is my original, right? The first one is my original, the same as one I plot over here. This one will be double sideband suppressed carrier goes through my spectral filter. So I have upper sideband modified. Right? This one I have the other side of upper sideband modified. When I do the demodulation, this part move to 2FC, right, and back to DC. This one. Demodulation, the signal time cosine omega CT again. So this side move to -2 FC. Back to DC. So here comes why we want symmetry. So this portion right will just recover the missing part of your signal lose because of less scale sideband. So the green one will cover the red part. The other side, same, right? The red one will cover my missing part by the less scale sideband, the outside. So I kind of recover my original message in frequency shift. So using west scale sideband, if you look at your modulated signal, right, does not like your original message at all. However, when we do the reconstruction or demodulation, your original signal is reconstructed. So the tricky thing is the filter shape, right, the filter shape. And we know, right, this one looks like maybe second order or third order, but it's filtered much easier compared with the ideal or very, very high accuracy, right, low pass filter. So the good thing compared with single sideband, easier to generate, right? You don't worry about phase shift, right? And you don't care about if there's DC components. The bad thing is the bandwidth is wider, right, compared with my original signals bandwidth. So I want you to remember two things. One is the special shape of the filter. Other one is the pros and cons. Right? Pros, we have either modulated transmitter side. The cons, the bad side will be the bandwidth is a little wider compared with single sideband. Any problems, questions? So in this one, we don't have equations, right? We don't have to calculate power bandwidth, anything. So just those 2 points. Y filter symmetry where we talk about. So we can have distortionless demodulation, circulation downshift spectral and circulation in phase. So cover that distortion with introduced by the filter. Okay. So this is a summary for the full member. After this, we have another very important topic. How good is the performance of my system, right? We talk about power, we talk about bandwidth. We also want to know when you listen to the radio signal, right? It's good or it's bad. So we talk about signal to noise ratio for all of them. So AM is modulation linear in terms of spectrum. In this family, we have, if you find AM only means double sideband large carrier. This is the most widely used technique. Double sideband subtracted carrier, single sideband, and vestigial sideband. Equation sketch in time domain for first two. Right? Equation sketch in first domain. I believe all of them you should be, you can do it. And we are going to have practice, so don't worry about that. Phasor diagram, average power, efficiency. I'm going to have summary later as we did for chapter 2, 3, and 4. So now we talk about this one. So we want to talk about how good is performance of communication system. So for analog communication, right, we talk about this one, I believe we talked about this one before, right? So how can we tell an analog communication system is good or not? We use signal to noise ratio. So compare with your original signal, noise higher, right, system is no good. When you listen to it, you will feel right, really bad, right? When noise compared with signal is small, you have good reception. And when you hear it, right, you also feel much better. So signal to noise ratio is a very important parameter to tell how good is your analog communication system. Later we talk about FM, right? Why FM? Listen to FM much better because signal to noise ratio is way more higher compared with AM. For digital, okay, we don't talk about signal to noise ratio anymore because my message will be coded, right, and sent through a channel as bit 1, bit 0. So for digital communication, we care about BER, bit error rate. Lower bit error rate means your system is better, right? Higher bit error rate means your system is worse. It's worse. And generally for the wired communication like optical fiber, cable, right, twisted telephone wire, give us pretty good bit error rate. For wireless communication, you can imagine, right? Not very good. Not very good. So all those techniques, right, we use the most likely implemented for wireless communication. For example, channel coding, right, source coding, equalization, spreading, and interleaving. So because wireless channel is really challenging, right? Noise, interference, right? Jammers. So from everywhere you have different things to interrupt with your channel. So we talk about signal to noise ratio for AM system. So generally we have the receiver. Signal off and noise out. So we're going to compare, right, signal in compared with noise in, signal out compared with signal out. If my receiver can improve the ratio from input, right, you're going to have better, right, reception. If it cannot improve anything of your signal-to-noise ratio from input, this kind of modulation method is not, it's not very good. So for example, right, generally we can consider the noise is pretty much the same, right, in same situation. Signal power, right, depending on how much power you send into your transmitter antenna. So for example, this one is at in. For example, this one, we have a fixed number, right? Using different receiver, different transmitting method, my signal noise ratio output can be higher, much higher, equal or even worse. So today we talk about AM, this one will be equal, a little bit better, or even worse. But for FM, this one will be much higher compared with your input. So similar as like CDMA, right? CDMA will kind of dig your message from the noise from inputs. Okay, so here, some mathematical stuff. Try to follow me. If you think it's really hard, don't worry. I want you to remember the final result. I'm going to highlight those things. So we talk about signal pass my system and noise pass my system. Okay, so here we talk about noise, right? Remember, chapter 4 we talk about noise. So here we view noise as a random noise. It has real parts and imaginary parts. Okay, here EJ omega 0 T will make our noise narrowband. So like we modulate my noise around carrier, right? Omega 0. This one will be the same as my omega C. So noise will operating in the same bandwidth with your signal. Okay, just look at the real part, the entire signal's real part. Okay, we have NC cosine omega 0 T from here, right? NS sine omega 0 T. So this is my real part expression for narrowband noise. Okay, here, this is my input, right? My noise will go through receiver, So for my noise. Okay, so noise mixed with cosine omega C, this is my receiver, right? So noise mixed with my carrier. Just time cosine omega CT to the right side. We get this one, right? NCT cosine square, sine and cosine. Now it will pass low pass filter, right? Low pass filter, we know this one is sine 2 omega 0 T, right? We are gone. This one we have 1 plus cosine, 1 plus. So this one we have. Here we are going to have half, right? 1 plus cosine 2 omega 0 T. This one will be sine half, right? So go through low pass filter. 2 omega 0 T is gone, right? Sine is also gone. Only this one left. So my output for noise goes through this coherent detector or coherent receiver. We have half NCT. Okay, the procedure is not required, but you do not try to follow. So this is my input, right? This is my output. I want to know the noise power, We try to calculate the power of it. Now we look at what about my signal power compared with noise power. Okay, over here. So we're going to evaluate 3 different receivers: single sideband, suppressed carrier. Double sideband, suppressed carrier, single sideband, and double sideband, large carrier. VSB is really complicated, so we skip that one. So double sideband, suppressed carrier, right? Signal in, signal out. So we talk about signals power. Then we just mentioned that noise power. So my signal power. This is my input, right? Input is message times cosine omega CT. We calculate the mean square value of it. We know it's half, right? The signal power, half came from cosine omega CT. Output. Remember we talked about output of the signal when we discuss the receiver side. Okay, so here, right, my output of this receiver will be half ACB. AC is amplitude of your carrier. B is amplitude of your mixing, right, signal. So if A, B, they're both equal, 1 will be half. So that is why we use half. My output signal is half FT. We carry this one's power, we get 1/4, right? Your signal power. So compared with my input, my power drop 50%, right? 3 dB drop for my signal. And for this one. Output signal is half FT. So output signal power will be 1/4, right, of my original signal's power. Compared with input and output, my signal power dropped, right, by 50%. This is for signal. signal, right? My input signal is NC. Let me write down. So NC. So here is N. So my input is NC. When it mixed with reference carrier signal, right? We talk about this one. We have high frequency components, another high frequency components, and DC value. Goes through low pass filter, my output will be half NCT, half NCT. So input is NC, output is half NC. So what will be the power? 1/4, right? 1/4. So for noise power, PN in will be half. No, will be so out input power will be NC square, mean square value. Out will be half, not half. Half NCT is mean square value. So this one will be 1/4 of my noise in power. My signal power drop 50%, noise power drop 75%. Right. Last slide mentioned my signal, right? S I, S N, S O, S R, right? S I. Last slide mentioned my signal power drop, but my noise power drop even further. So for double sideband suppressed carrier demodulation, this one is remember. So for double sideband suppressed carrier, I can increase my signal to noise ratio compared with input by 3 dB, right? 3 dB. So 2 times. So a little bit higher by using double sideband suppressed carrier. Please remember the result. Previous analytical part, right? So actually this one is the best we can achieve for AM family. Okay, here I have 2 more things from you here. For single sideband, there is not getting any worse, not getting any better. Signal to noise ratio at my output will be the same as my input. So the same, does not change anything. However, for double sideband large carrier, if we use envelope detector for sinusoid modulation case, if your signal is sinusoid case, your signal to noise ratio compared with input is even less, right? So 2m squared over 1 plus 2m squared times of SI over NI. So if m is pretty small value, right, your signal noise ratio will be worse, much worse compared with your input. So this is also the reason why people use very, very high power for the transmitter, because it can make this SI to NI pretty big, right? When it reach your receiver side. So then after the demodulation, we still have something we can listen, right? We can distinguish it's music, right? Or it's speech or anything. So after you remember those 3 equations in red circle: double sideband, double sideband large carrier, single sideband, and previously this one, double sideband. summarize chapter 5. If you have any problems, please let me know. So, summarize for chapter 5. Chapter 5. The first one we talk about in AM family is large carrier, right? So double sideband, large carrier, AM. So first, I want to talk about in time domain, right? What does it like, and how can we express it in equation? So this is equation for double sideband large carrier. So this is time. This is time. This is time. Okay, A is my amplitude for my carrier. M we call it modulation index. Omega C is my carrier frequency. Okay, I also ask you to plot, right, sketch in exercise, examples, and your homework. So if I sketch it. The envelope of my signal will be very close to the message FT. And inside is your oscillation of sinusoid. All those amplitude of your envelope related with A and M. Remember how we calculate those things, right? So this is time domain. Signal for double sideband, large carrier. Frequency. Okay, frequency domain we have So in frequency domain, my Fourier transform of this given signal, it has two impulses from this one cosine omega ct. So we have pi A, right, two impulses. And we have original signal, spectral move to omega c and So spectral of my double sideband large carrier. We have those two large carriers, right? Omega c minus omega c and your original signal here and over there. Okay, so we talk about time and frequency, right? Both time frequency equation sketch. Then we talk about how can I generate my double sideband large carrier. So they have double sideband large carrier modulator like this, looks like this, right? You have signal mixed with cosine omega CT here, right? Here. And you have the pure carrier added, right, to the modulated signal. So this is my modulator side. Okay. Demodulation for double sideband large carrier. We mentioned they use very low detector. So we use envelope detector to demodulate my signal. This detector is very simple, so very cheap, right? Cost really, really low. This is the only good thing for this technique. All others, right? We're going to talk about power efficiency and signal ratio very soon. Power and efficiency. Okay, the total power has two parts. Half A squared times 1 is my carrier power. Half A squared M squared message power is my PS, the PS. So this is my total power. Okay, so my efficiency is PS over total. This is my efficiency. We show several examples, right? The efficiency is pretty low, right? In example from our textbook, 20%. In the real application, efficiency around 5%. So very, very low efficiency. Bandwidth for double sideband large carrier is 2 times, right? It's 2 times of your original message bandwidth, so double, right? Double. Last one is the one we just talked about. So the signal trend ratio for double sideband large carrier is we use envelope detector. This here, 2m squared over 1 plus 2m squared input signal power. So this is almost everything about double sideband large carrier. Okay, this one is too low, right? So very low. What can we do? We have second one to improve my efficiency. So we have double sideband suppressed carrier. So this is my motivation for suppressed carrier. We want to improve my efficiency. Okay, so So here we have the second one. Double sideband. B as B, as C, as C. So in time domain, my equation is even simpler compared with double sideband large carrier. Just A, Ft, cosine omega C. So this is my time domain equation. This time, the blue one actually is similar to your original signal. However, my envelope, including the blue one and green one, does not look like my original signal at all. Also, okay, when you plot the waveform in time domain, remember every time your signal pass 0, there will be a phase reversal in your carrier. So there is phase shifted by 180 degrees every time the signal pass. We call it phase reversal. So this is time domain signal equation and sketch. So it's also required, the sketch. This is my spectrum in frequency domain. You can just use the property, right? Property of free transform. So here we have frequency domain equation and sketch. Okay, my transmitter side will be a part of your large carrier, right? Just signal mixed with sinusoid. We get double sideband surface carrier. So transmitter side, right? No extra work. However, for my demodulation, so my demodulator will be much more complicated. Double sideband. So the signal go to my receiver. We have to go through a coherent detector or coherent demodulator. So mix, right? Low pass filter, 2-step. In order to find perfect reference signal to mix with your receive signal, we need to use phase lock loop for phase and reference expression for frequency, right? For frequency. So for this one, my receiver is much more complicated compared with double sideband large carrier. The total power is half, right? A squared, the message power, half still from cosine omega c. And look, what did we do, right? We really improved this efficiency from 5% to 100. So now my efficiency is 100. All the power I used transmitting my information. So this is our motivation. And this is when we really achieve the goal. Okay. However, my power still, my band is still 2 times of original signal's bandwidth. And will be 2 times of okay. Signal to noise ratio. My output signal to noise ratio is 2 times of your input. So my performance will be better compared with large carrier. So this is what we gain, right? We gain better efficiency. This is what we pay, right? More complicated receiver side, demodulating part of the system. Okay. Even I have 100% freezing. Problem.
What? I never caught what M and D stand for.
M?
M and D, the two columns.
Modulation, demodulation.
Modulation. Yeah. Modulation. And demodulation. Demodulation. Okay. So here, we know bandwidth is important, right? Bandwidth is expensive, so 2B, we still want to improve it. This is the motivation for next member here. For single sideband, right, we want to improve my efficiency for bandwidth, right? Because we know no matter you have lower or upper sideband, can cover all the information in your message. So next member, the most advanced, right? Most advanced, we call it single sideband. Single sideband. Okay, equation. Single sideband can be expressed by, in tandem can be expressed by phase shift method. So signal mixed with cosine, signal with a 90-degree phase shift. Here what transform of your signal mixed with sine omega ct plot, right? No required for general signal. If it's sinusoid, right, you can do it for other signals, no required. Okay. Frequency domain. Equation, right? We didn't talk about equation at all, so I'm not going to ask you for the equation. However, this one will be, let's see. And lower second. So for lower sideband, we are going to have just half of your suppressed carrier. If the floating component is higher than omega, so you call the upper sideband. Oh, minus plus, right? Minus plus, we get